Welcome to problem solving session for the course Linear Algebra. I am Siddhi Balu Ambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 3, that is problems related to Echelon form and Gauss elimination method. So let us start with the first problem. Yes. Let A is equal to this matrix 2x, x, 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 and 8, 7x in M3R. So this notation means 3 cross 3 matrices over R. And when I say over R means all the entries are from real numbers. And we have to find at least 3 real numbers x such that the linear system of 3 equations in 3 variables Ax is equal to 0 has infinitely many solutions. So this is the question. So I hope you all know what it means when a system has a solution and infinitely many solution. So when they are writing this in this form, this Ax is equal to 0, what does it mean? It means this is the matrix 2x, x, and this is, suppose this X matrix here is x1, x2, x3 is equal to 0, 0, 0. This 0 here means the column vector 0, 0, 0 in R3. So what it means is this is system of equations such that 2x1 plus x2 plus x3 is equal to 0 and so on. So this, when we have this 0, 0, 0 here, it is called as homogeneous system of equations. Okay, and if this, instead of this 0, 0, 0, if there is some non-zero vector x, ABC, non-zero in R3, then it is called as non-homogeneous system of equations. Okay, so here we have a homogeneous system of equations, and what we have to do is we have to find the value for this x here. Here means all this x simultaneously, such that this system of equation now has infinitely many solutions. And so how will you proceed for that? See, note that whenever we have this kind of system, Ax is equal to B, this B is in R3 or any K, and this A belongs to my M3K or MNK, whatever system we have. the moment we have when, and this is what we need to find, this x, the what we say column of variables. Okay, we have to find values for this variable such that this system is satisfied. So if this is my epsilon, then I need to find this solution set of epsilon. That is, I need to find this x in, this is not correct way, this v is in kn and this x is in kn. Okay, when I write this, I assume that this is column vector. Okay, because often when we write Rn or some Kn, we assume it to be row vector, but when I'm writing this here, I'm assuming these to be column vectors, and this x also is variable vector. I need to find this, so we need to find this x here. So note that whenever we have this a in M and K, we are talking about, this is, when I'm writing here M and K, it means this is square matrix. And the moment I have square matrix, I can talk about this invertibility. Okay, the moment I have this system of equations where number of variables and number of equation are equal, in that case, this A becomes square matrix. And in that case, whenever this M belongs to M and K is such that this determinant of this A is invertible, then epsilon has unique solution, right? Because the moment I have this ax is equal to b and I need to find this a, and a is invertible, so I can always take this, right? A inverse b, and this will be the solution. This x is equal to a inverse b will be solution of the solution of epsilon, or yeah. So, but the moment, so this is the case when I'm talking about what we say system where b is non-zero, okay? And the apart from that, when I want to talk about ax is equal to 0, just a second, ax is equal to 0, and again when this what I say, when this a is invertible, then this x will be a inverse b, and this b anyway is 0 here, so x will be just 0 0 0, I mean all the zeros, and this will be unique solution for this homogeneous system of equations. So the homogeneous system of equation epsilon ax is equal to 0 has unique solution, namely or particularly this, the 0 vector in K, this is 0 vector in Kn, if A is invertible matrix. And note that in case of homogeneous system of equation, it will always have a solution 0 0 0. Okay, that is always there. So in general, if you see the questions, they have asked many questions where find value of some variable where we have no solution, infinitely many solution, or unique solution. But in case of homogeneous system of equation, we always have a solution. There is no, I mean, we cannot have situation where there is no solution, because 0, 0, 0 will always be a solution for the homogeneous system of equation. So either we have unique solution or we have infinitely many solution in case of homogeneous system of equation. So let me just write this down. Note that in case of homogeneous system of equations, we do not have have or let me write it. We always, the system always has a solution, namely this, the zero vector. And the system has unique solution if, let me say, unique solution if A is invertible and it is not, and or no, and it has infinitely many solutions if A is not invertible. And how to see that this will all, these two are the only cases? Because see, when we write any matrix here, this not matrix, yeah, matrix. For example, suppose I'm writing this a11 into a1n, x1 up to xn. This is equal to 0. This is a21, a22, a2n, and so on up to an1, an2, and ann, right? If I try to write this matrix in something of this sort, this a11, a21, an1, x1 plus a12, a22, an2, x2, and this a1n, a2n, ann, xn is equal to 0, 0, 0. Then if I consider this to be element from Kn, so what it means? These are, since I'm talking about n cross n matrix, this is n cross n matrix. This becomes n vectors in the space Kn, right? And now when I'm writing this, I'm talking about its linear independence or dependence. Okay, the moment I have the matrix, if this, the only possible solution to this, if it is 0, then this matrix here becomes invertible because this, all the vectors becomes linearly independent. Okay, and when I say I have non-zero solution to this matrix, then these columns are dependent on each other. I have linear combinations such that when I do that, I get a zero matrix. And in that case, I will have some non-zero linear, I will have some non-zero solution. When I put them here, it will be non-zero linear combination of n vectors giving me 0, 0, 0. It means those n vectors are linearly dependent, and the determinant of this matrix will be 0 in that case, because you know that when we do what we say, mm, row operations or column operations, uh, the determinant does not really change. It changes when we swap the columns, but when we do addition of two vectors or subtraction of two columns or rows, in that case, the determinant does not change. And thus, if the determinant is non-zero, it remains non-zero. If it is zero, it will remain zero after those adding, subtracting, the linear combination when we do of the column vectors or row vectors. So the question here is, so I hope you understood what I'm trying to say here. When we talk about homogeneous system of equation, it really boils down to whether the matrix, when we talk about the system AX is equal to 0, we have to see whether the matrix A is invertible or not in that case. That's what I'm trying to highlight here, because that is what will help us here, because what we want to find here is infinitely many solution to this system of equation. So what I will do is I will try to find whether this matrix is invertible or not. And we know that if a matrix is invertible, its determinant is non-zero, and if it is not invertible, then its determinant is zero. It's if and only if condition. So instead of going to row echelon form and looking at everything, and there is only one variable here which we need to find, this x. So instead of going to row echelon form, what we can do is we can make use of this information about invertibility of the matrix, and we will check whether the determinant is zero or not, or for what values of x the determinant is zero. And those will be the exact x for which I will have infinitely many solutions to the system of equation. I hope you understood what we are going to do here. Is it okay? So the matrix here was this. Let me just copy this matrix here. This is my x. Okay. And what we are going to do is we are going to find the determinant of x. So this is my A, and the system AX is equal to 0 will have infinitely many solutions if determinant of A is 0. That is, we need to find the value of x such that determinant of A becomes 0. Any doubt here what we are trying to do and why we have arrived at this condition here? Okay, so now I will just try to find determinant of this matrix. And this is 2 into x square minus so if let me just calculate. Minus x square minus plus 8, and this is minus x. So this is x. I hope I am calculating it correctly. This is 8x, yeah, 8x here and x. So this is x square. So this, okay, let me just, this is x square, or this 10 minus 9x 2 plus 9x minus 14, and this is minus x. So this is minus x into x square minus 9x plus 14. So this is x minus 7 and x minus 2, if you check correctly. Yes. So therefore, A will have infinitely many solutions if this, if minus x, x minus 7 and x minus 2 is 0. And when will that happen? And this is possible only when we know that x is equal to 0, x is equal to 2, or x is equal to 7. Is this okay? Any doubts here? Okay, it's yeah. So yeah, that's what I wanted to show here, that we can heavily make use of this determinant property whenever we are trying to find answer or solution to such kind of questions where we are asked to find value for particular variable. So instead of going to all row echelon form and everything, which I mean, if we have like bigger matrices where 4 cross 4 or 5 cross 5 matrices are given, in that case, finding determinant itself is pretty difficult. But other than that, in such situations where only one variable is, we have to find value for, in that case, you can use this determinant condition in case of homogeneous system of equation, or even in uh, what we say, even in non-homogeneous case, if you are asked whether the given system of equations has a unique solution, no solution, or infinitely many solution, in non-homogeneous case I'm talking about, even in that case, the moment you have invertible matrix, the solution will be unique. There won't be any other possibility for that. So if you want to discard one of the conditions in case of a non-homogeneous system of equation, in that case also you can check for invertibility of matrix A and then proceed accordingly. Okay, so yeah. So these are the only three. And in the question, they have asked that at least three real numbers x. Okay, and if you at least three real number x, but if you check, these are the only possibilities when this will happen. Uh, because we actually got this by doing proper calculation, that finding determinant of this to be 0 and so on. Okay, so these are the only three possibilities for x for which you are getting infinitely many solutions. You can put other values and check and see whether you are getting infinitely many solutions in those cases or not. Okay, so let us move to next question now. Yeah. So find the conditions on the element A, B in the field K such that the system Ax plus y is equal to 1 2x plus y is equal to b has no solution, one solution. So when we say one solution, this is what I mean when I was saying unique solution, and infinitely many solution. Okay, so we have to find conditions on A and B such that this system has either no solution, one solution, or infinitely many solutions. Okay, so what this system look like? So this is ax plus y is equal to 1 and 2x plus by is equal to b. So this is a1 to b, xy is equal to 1b. Is this okay? So I'm just writing this in matrix form. And as I said before, the moment, so if I call them ax is equal to this b and this b is different. So let me call this capital B, or let me call this D here. Sorry, here it was 1. So yeah, uh, as I said before, the moment I have invertible matrix A, the solution will be unique, because in that case, I can just take inverse of this matrix here, and this will be the only unique. Why this will be unique is because the inverse of a matrix is always unique. Okay, because yeah, that's there. In matrix, in matrices, if inverse exists for given matrix, then it will always be unique. Okay, so uh, one thing is that the matrix multiplication is not commutative. So in general, AB is not equal to BA for is not equal to BA for what we say in matrices. If A and B belongs to some Mn, yeah, Mnk, then this is not true in general. But the moment I have AB is equal to this identity, then BA will also be equal to that same identity. I mean, not the same, I mean, identity. So when the inverse exists, it will always be unique and it will commute. So if AB is equal to IN, then BA will also be equal to IN. These things you need to take, I mean, just think properly about this. So that's why this inverse of a matrix is always unique. And that's why when I take A inverse and multiply this on the left side, on the right side of the equation, it will give me the solution for this non-homogeneous system of equation. And when will that be invertible? So what I want is this A minus, so this A epsilon will have unique solution or one solution if A is invertible. That is, determinant of A is non-zero. So in that case, what I want is, that is A minus 2, I want this to be non-zero. So this implies A to be non-zero. Okay, so therefore, epsilon will have, and note that in this case does not matter what B is. B could be anything. B could be anything in my field K, or yeah, my field K, and this will still hold, because in that case the matrix A has inverse and I'm multiplying by the inverse here and I'm getting the unique solution, the one solution. Therefore, epsilon will have unique solution. Oh, sorry. This implies A to be not equal to 2. Unique solution if A not equal to 2 and B is any k in R. So A belongs to K such that A not equal to 2 and B in K. This is the only condition we need for system to have unique or one solution. Okay, so now the condition where A we wanted to be not wanted to be. So the condition where A is invertible, we get that the system will always have a unique solution. And we are through this one. We already found the conditions where the system has unique or one solution. Now, what about the rest? So we already saw. So the invertibility took care of the uniqueness part or the one solution part. So the rest are no solution or infinitely many solutions. So in that case, so one condition where A not equal to 2 is done. So now in both these cases, A will be equal to 2. Okay, and based on that, we have to see what value should we take in K such that the system will have either no solution or infinitely many solution. So that is the next approach to find the no solution or infinitely many solution part. So here now when A is equal to 2, then the system becomes 2, 1, 2, 1, x, y, and this is 1b, right? So this is what this is 2x plus y is equal to 1 and 2x plus y is equal to b. And note that if solution, this is my epsilon, if solution of this, sorry, this is b, system of equations exists, say x naught, y naught, then it will satisfy both the, if I call this equation 1 and if I call this both the equations simultaneously. So it will imply that I have, that is 2x naught plus y naught becomes 1 and 2x naught plus y naught becomes b. So then, so this will imply what? That b needs to be 1 when the solution exists. Okay. So hence if solution exists, then b has to be 1. And once I have b is equal to 1 and hence, and as b is equal to 1, we are left with only one solution, one equation. Two x plus y is equal to 1. And in that case, it has infinitely many solution as well, right? You just vary the value of x and you will get infinitely many y here. And in this case, we have infinitely many solutions. So what is the condition here? Hence, when A was 2, so we are starting from this here. When A is 2 and B is 1, then the system has infinitely many solutions. Is there any doubt here? Like, first we started with A is equal to 2, and then we assumed that if the solution has to exist, then my B becomes 1 here. Okay. And once my B is 1, instead of 2, now my system has only one equation, because these two equations now become one equation, and that will give me infinitely many solutions. Precisely this in this case. So now, so if solution exists, then B has to be equal to 1, and hence if A is equal to 2 and B is not equal to 1, then the system does not have any solution, because in that case this 2x naught, if solution exists, then this, say, x naught y naught, then this 2x naught plus y naught becomes 1, and 2x naught plus y naught becomes b, and which we are saying is not equal to 1. So it is like 2x naught plus y naught. So this is like 2x naught plus y naught is equal to 1, but this is not equal to b, but this is equal to 2x naught plus y naught. So this is not true, or not possible, or does not make sense. Okay, so that's why when hence A is hence if when therefore when A is 2 and B is not equal to 1, the system epsilon does not have any solutions. Is this okay? Any doubts here? And note that it also covers all the possibilities of A and B. So A is equal to 2 and A not equal to 2. So when A was not equal to 2, I got unique solution. And when A was equal to 2, the B had two possibilities. B was either 1 or not 1. The moment B was 1, the system had infinitely many solutions. And when B was not equal to 1, the system did not have any solution. Is this okay? So it actually covered all the possibilities of this A and B, and we got the conditions on A and B such that all these three possibilities happen. That it has no solution, unique solution, and infinitely many solution. Any doubts here? No doubt. Okay. We'll move to now next question. Similar kind of question. Yeah. So they're going to find the conditions on the elements A, B, C in a field K such that the system x plus ay is 0, y plus bz is equal to 0, and z plus cx is equal to 0. Okay, the reason I wrote this because it will be easier for us to write it in the matrix form. Has no solution, one solution, and infinitely many solutions. So, can you tell me whether, so this is what this is, if I want to write this in this form, the compact matrix form, it is 1A0, 0, 1B, C0, 1, X, Y, Z. Can you tell me the conditions where the solution will not exist? The first one. This is homogeneous system of equation. So when can we say that the system will not have a solution? Is it possible that system will not have a solution? It's not possible. We also saw this in the very first question where we were discussing the homogeneous system of equation. And as I said before, every homogeneous system of equation has solution 0, 0, 0. In this case also, the 0, 0, 0 will always be the solution to this system of equation. So since epsilon is a homogeneous system of equations, it always has a solution. Okay. Hence, no A, B, C in K, no, what we can say, yeah, possible values of A, B, C can be in K such that epsilon does not have, epsilon has no solution. Okay, so system of equation, sorry, homogeneous system of equation will always have a solution. I hope that's clear. Please understand this very clearly. To check, whenever you get some, whenever you see the solar system of equation, please check whether it is homogeneous or not. If it is homogeneous, then there are only two possibilities: either unique solution or infinitely many solution. Unique when A is invertible, and that unique solution is 0, 0, 0. And if the matrix A is not invertible, in that case we get infinitely many solutions. But 0, 0, 0 is always the solution for homogeneous system of equation. So yes, in this case, no solution is not possible. Okay, so no solution is not possible. I'm writing here, not possible. So now there are two conditions left. Either A is invertible or not invertible. So, and how to do that? Using the determinant. It's easier that way. I mean, you can do all the row echelon form and everything, but I feel for home, I mean, for such, to guess whether system has solution or not, and to find values of such A, B, and C, such kind of questions, it's easier to go through this method of looking at the inverses and so on. Okay, so let us start with. So we have to check when the determinant of A is 0 or not. So suppose A is this matrix 1A0, 0, 1B, C0, 1. Let us just calculate determinant of A. It will be, I hope I wrote the matrix correctly. 1, 1 minus 0 minus A into 0 minus BC plus 0. Okay, and this is 1 minus A into minus BC. So this is 1 plus ABC. So hence, therefore, if determinant of A is 0, the system will have infinitely many solutions. That is, if A B C, sorry, A B C plus 1 is equal to 0, that is A B C is equal to minus 1, then the system will have infinitely many solutions. Is this okay? So the condition under which I get the matrix has infinitely many solution is when ABC is minus 1. Okay, and if determinant of A is non-zero, the system will have unique solution. Namely, this. That is, if ABC plus 1 is non-zero, that is, my product, this ABC, is not equal to minus 1. Then the system has unique solution. Is this okay? Good. So I hope so far it was easy to understand, like how to go, because we are dealing with homogeneous system of equation. It becomes easy. And yeah, I mean, and this specification of ABC is enough for you to conclude whether the system has unique or infinitely many solutions. I hope this was okay. So let's move to next question. Yeah. If this is that we will do. This one is this is I think question 4. Yeah. Let K be a field of characteristic not equal to 2. That is 1 plus 1 is not equal to 0. Yeah. In K, and let A belongs to K, we have to compute the solution set of the following system of linear equations over K. So, and the systems are ax1 plus x2 plus x3 is equal to 1, x1 plus ax2 plus x3 is equal to 1, and x1 plus x2 plus ax3 is equal to 1. This is 1, and x1 plus x2 minus x3 is equal to 1. 2x1 plus 3x2 plus ax3 is 3, and x1 plus 3x3 is 2. And and the question is, for which A these systems these systems have exactly one solution. And when we say exactly one solution, can someone, ma'am, please explain again? No solution. Okay. Infinitely. Okay. So, yeah, for this question, uh, I said that it is not possible to have no solution, because see, these are three. See, this is homogeneous system of equation. I want to find x, y, z such that it satisfies. So what does this mean? Let me just write this using this one. So what does this mean? This x plus ay is equal to 0. This x plus ay is equal to 0, y plus bz is equal to 0, and cx plus z is equal to 0. This system of equation must have solution. Okay, and does not matter whatever a, b, c are there. This 0, 0, 0 will always be a solution to this equation, right? 0, 0, 0 does not matter whatever this a, b, c are. This, let me just write this again here, maybe somewhere, that for, or let me write this in a red pen only, that for any a, b, c in K, this 1, 0 plus a 0 plus 0 will be 0, right? I'm writing this in bracket. 0, 0 plus 1, 0 plus b 0 will be 0. And c 0 plus 0, 0 plus 0, 0. So this implies for any ABC, 0, 0, 0 always belongs to L of epsilon, right? 0, 0, 0 is always the solution of this system of equation. Does not matter what this A, B, or C here are. So that's why this is the no solution case is not possible, because 0, 0, 0, or does not matter vertically or horizontally, is always the solution of epsilon. This is my epsilon method. Is it okay now? That why no solution is not possible? Because 0, 0, 0 is always the solution of this equation. Does not matter what ABCs are. So you choose whichever ABC from this K, that ABC will always give me at least one solution for this system of equation, and that is 0, 0, 0. Okay, so that's why it's not possible to have ABCs such that this system is not having 0. Okay, it's clear now, I hope. Okay, So not possible because 0, 0, 0 is always solution. So there are only two possibilities when we talk about homogeneous system of equations. So when we talk about non-homogeneous system of equations like this, in the second question which we discussed, where this is not equal to, let me write this with this way. This is not equal to 0, 0. So the given system is not homogeneous. Okay. And that's why when we tried to find the conditions, so for all these conditions, no solution, one solution, and infinitely many solution, I had some conditions on ABC. I mean, the possibility was there that such system would exist in this case because the system was not homogeneous. But yeah, we saw these three conditions where this was one where A was not equal to 2, this A not equal to 2 condition for, let me write, sorry, for unique solution or one solution. This, let me use this pen. This A is equal to 2. But with this A is equal to 2, when I had B is equal to 1, this had only infinitely many solution. And when A was 2, but B was not equal to 2, this case is no solutions case. Okay. So all three were possible because we were talking about non-homogeneous system of equations. But when we have homogeneous system of equation, 0, 0, 0 is always the solution. That's why the only possibility where, even if, I mean, if at all we have to find such ABCs in the question, such possibilities for ABCs are possible when in only these two cases. Let me just box them. This one and this one. Infinitely many, or no. Let me, possible only when this case. One is solution and infinitely many solution. So possible to have ABC in K. I hope now it is clear. So system of equations when homogeneous and non-homogeneous, they work differently and they behave differently. So yes, now again we are back to the condition. Here again, if you see, there is only one variable A, and we have to again find, and they have already asked that we want to find the condition on A where we have exactly one solution. So after discussing these three questions, we are on the fourth question. So what is the condition where we have exactly one solution? Can someone please tell me? So when I'm asking this question, I mean that when I write this system in this form, X is equal to B, what is the condition on A for which I will have exactly one solution? Can someone tell me? So as we saw, the only
Determinant A
case,
not equal to 0, madam. Then,
exactly, determinant A not equal to 0 or A to be invertible. Exactly.
madam.
So that is the only condition where such case is possible. So what we need to do is we have to write this in again matrix form, calculates its determinant, and the determinant must be not equal to 0. That is when the matrix will be invertible. and we will get the solution is unique. Okay, so that's what we will be doing even here. And here they said that what are the values for this A where the solution is exactly 1. So for the first one, let us write the matrix. So A here is, sorry, is A11, 1, 1, and here it is, sorry, 1, 1, and A. And yeah, so let us solve for this one first. Let me give them numbers. So determinant of A, I will add that note later, but yeah, for now let us focus on this. This A into A square minus 1. So this is A into A square minus 1 minus this is A minus 1. This is minus A minus 1. So this is A square minus 1 minus 2A minus 1. So A square minus 1 is A plus 1, A minus 1 minus 2A minus 1. So this is, if I take A minus 1 common here, it is A plus 1 minus 2. So this is A square plus A minus 2. And so this is A minus 1. And if we simplify this, what do I get? This needs to be 1. So plus 2 minus 1, right? So this is A plus 2, A minus 1. Oh, A minus 1, A plus 2. So A minus 1 square we got here. Okay, so the only possibility when, therefore, and we want the solution to exist. So I want, so the unique solution exists when the determinant of A is not 0. That is, this A minus 1 square into A plus 2 is non-zero. That is when A is not equal to 1 and A is not equal to minus 2. So these are the two possibilities. Except for these two, therefore, for any A in K with A not equal to 1 and A not equal to minus 2, we have the system, we have system with the unique solution. Is this okay? We want determinant to be non-zero for matrix to be invertible and hence the solution to exist. So that's what we did here. So for this to be non-zero, I want A to be neither equal to 1 nor equal to minus 2. In that case only, I will have that the matrix A is invertible and the system has solution. Is this okay? I mean, this exercise is very calculation heavy. So yeah, so you need to do the calculations, and mostly the all the questions are related to such kind of questions. I mean, So far what we have discussed is just looking at the invertibility of matrix and arrive at the solution. But we will see questions where we actually have to use row echelon forms and so on. Let us finish this one first. Yes, so and now the second matrix was this. For second one, A is 1, 1, minus 1, 2, 3, A, and 1, A, 3. And now the determinant of A in that case is 9 minus A square. So if I calculate this, this is 3 minus A, 3 plus A, minus 6 minus A, minus 2A plus 3. So this is minus 3A. Sorry, this is plus. This is plus A. So this is minus 3 minus A. So this is 3 minus A, 3 plus A minus 3 plus A. So 3 plus A. So this is A plus 3 minus A plus 2. And if I take minus outside, it is A plus 3, A minus 2. I hope I did not mess up anywhere, I assume. And so therefore, the system has unique solution when determinant of A is non-zero. That is, again, this minus A plus 3 and A minus 2 is non-zero. That is when A is not equal to minus 3 and A not equal to 2. Therefore, the system has unique solution only when A is not equal to minus 3 and A is not equal to 2. It's similar to what we did in earlier case. But I hope now you understood like how to go with such kind of questions. And if you see there are many such questions in your assignment sheet, like if you look at this question 3.5 from the assignment sheet, if you have it with you, it also deals with a similar kind of question, and it asks you for the conditions for A where the solution exists, solution does not exist, or infinitely many solutions exist. And after that, it asks you to find the solution for those system of equations. So let us just try to do that so that we also get to solve a question where we are actually finding the solution of the given system of equation. And then we'll move to a few more questions. Yeah, let us do this one first. This is question, I think, 5th. So I won't be explaining much. We will just go into the calculations directly because we already know that what we need to do to tackle such questions. 2ay plus 3z is 2. And again, the question is for which values of a linear system, this epsilon a. Epsilon a because system depends on a, has first no solution, second exactly one solution in R3. Okay, they are talking about R3. And third is infinitely many solution or more than one solution in R3. Okay, and second is that find the solution set L epsilon A. Okay, so let us see how it is going, how it goes. Okay. So again, to no solution, exactly one solution, we have to again find the determinant. So if I write this in this form, in order to, so note that here again, in order to find exactly one solution and more than one solution in R3, it is not enough to conclude just that A is 0 and A not equal to 0 case. We actually need to find the conditions on A where. So what I'm saying is, in this case, we actually have to go to row echelon form, the augmented matrix, and see how A behaves there and what we get. I hope you know what augmented matrix is. So this matrix, and see how whether it is and how it looks. We will see the conditions later on, but for now, let us calculate A and its determinant to at least have condition where the solution exists, and when we have one solution, exactly one solution. Okay, so A is my matrix 1, 1 minus 1, 2, 3, 2A. I hope I'm writing it correctly. And X, 2A, and 3. Okay, so determinant of A is 9 minus 4A square minus 1, 6 minus, sorry, it is 1 here. 6 minus 2A minus 1 into 4A minus 3. So this is 3 minus 2A, 3 plus 2A. And here I have 6 plus 2A minus 4A plus 3. And this is 3 minus 2A. So this is minus 3 minus 2A, 3 plus 2A, minus 3 plus 2A. And now I get this 3 plus 2A into 3 minus 2A minus 1. And this is 3 plus 2A and 3, so 2 minus 2A. So if I take minus common, this is 2A minus 3 and 2A minus 2. Okay, so hence the matrix, sorry, the system has unique solution when determinant of A is non-zero. That is when this 2A minus 3, this, that is 2A minus 2 is non-zero. Sorry, is non-zero. That is when A is not equal to 3 by 2 and A is not equal to 1, right? These are the only two possibilities. Please let me know if I'm missing the calculation anywhere. Okay. So yeah, these are the only I mean, when this happens, then the system has unique solution. And we can find the solution using this Gauss elimination method and so on. And when this A is equal to 3 by 2 and A is equal to 1, these are the only cases left. So understand that one of them will give us no solution, and the other one will give us infinitely many solution uh, if you have understood what we have been discussing so far. Okay, even the conditions on AB when we found in the very first or I think second question, this 2, A was equal to 2, A not equal to 2, then B had two conditions, B is equal to 1, B not equal to 1. It covered all the possibilities for A and B both. Okay, A being 2, B could be anything. Then when A was not equal to 2, no, A was not equal to 2, B could be anything, and we had unique solution. A was 2, then B is equal to 1 and not equal to 1 was giving me the condition for no solution or infinitely many solution cases. So here also, whenever A is not equal to 2 of this, A is in R, I think. Yeah, we are working in R here. Okay. So anything other than 3 by 2 and equal to 1 will give me infinitely many solutions. Sorry, will give me unique solution. The matrix A will be invertible in that case, and inverse of that matrix. So in this case, that is when A is not equal to 3 by 2 and A is not equal to 1. The matrix A will be invertible. And this X is equal to A inverse B. This B here this is my B, 1, 3, 2, will give us the unique solution. And how to find that solution? We know how to use row operations to obtain the inverse of any given matrix, right? So, and to find the inverse of given matrix A, we can use the row operations, not Gauss elimination method. Yeah, row operations. And so you know how to do that, right? We consider this A here. A will be now this same matrix. Let me just copy it. This is my matrix. I start with this identity matrix here. Okay. And I try to make this as my identity matrix, this as IN. And whatever operations I need to perform on this left-hand side to arrive at IN. So I hope what this IN means. This is identity matrix. This I3, sorry here. It is exactly this. When I convert this matrix into I3, whatever row operations I'm performing here, I will be performing the same operations here on right hand side. and the resultant matrix which I get when I get identity matrix on the left hand side is my inverse of this matrix A. Is that okay? I mean, you can solve it. I mean, let me just do a couple of steps, because if we try to do the entire thing, it will take up too much time. But let me just start with, because uh, we did not do any row operations so far. So let us do that. So yeah, so let us make this. We have to make this 0 and this 0. Okay, so we will do R2 minus 2R1 and R3 minus 2, sorry, R3 minus R1. And this will give me 1, 1 minus 1. This 0, 3 minus 2, 1. This 2a minus 2. So this is 2a plus 2. And here I am having 0, 2a minus 1. And this is 3 minus 2. So 5. And here I need to do, note that this, when I'm doing, I'm kind of keeping the row R1 fixed. Okay, I'm not, what I can say, I'm not doing, I'm not changing, like for example, in one step I'm changing R1 and R2 using R1 and R3, something like that. So when you are doing this, make sure that you are not making the changes to R1 again. So when I'm doing this and doing this, I'm keeping both. What I'm trying to say here, when I'm doing this operation here, I'm kind of treating R1 as some fixed quantity, and I'm changing R2 and R3 using that. I hope you have understood. So that's why when I'm writing the resultant matrix, my R1 are fixed and only R2 and R3 are changing. Okay, so mostly when you see in the book, they write it like this. R2 is equal to R2 minus 2 R2 and R3 is equal to R3 minus R1. So this is like, this is new row 3, which we got after doing this operation here. Something like that. So here again it was minus 2, 1, 0 and 0, not 0. R1 is minus 1, 0 and 1. Please let me know if I'm making any mistakes. Okay, and now note that I now no more use first row here. Okay, so, or we can maybe. And now what I will do is I will make this 0, because we want to go to what we say. If you make that 0, I anyway cannot use. Let us do make this one 0 first. So this R2 is, now I want to do R3 is equal to, this I want to make 0. So what I need to do is 1 minus 2a minus 1 R1. Sorry, R2. Right? So this will give me 1, 1 minus 1, 0, 1, 2a plus 2. And And now the third one changes. So 0 remains as it is. This becomes 0 because that's how I choose. And this is 5 minus, this is 5 minus 2a minus 1, 2a plus 2 into 2a minus 1. So this becomes 5 minus 4a square plus 4a minus 2a minus 2. So this is 5 minus 4a square minus 2a minus 2, plus 2a minus 2. So yeah, this, no, sorry, why did I erase that? So this becomes, and here it is mm, minus 1 minus 2 into, so this is minus 1 minus 2 into 2a minus 1. So this becomes minus 1 minus 4a plus 2, and this becomes 1 minus 4a. So this is 1 minus 4a, and this is 1 minus, we are subtracting, right? So this is 1 minus 2a, and this is just 1 here. Okay, so note that the way I am making this entry 0, this entry 0, this entry 0, in resultant matrix, I'm actually getting what I'm saying. Sorry. I'm actually getting the entries, the corresponding entries. So the moment I'm making the 0, 0, 0s here, the corresponding matrix here changing and giving me the corresponding entries of invertible matrix, and so on. And you can check that when you arrive at a situation where you have to, you know, do something like this, that you have to multiply some, maybe you have to make this one 0. So you will just multiply by this 1 minus some, two, just example 2a plus 3, and you have to multiply this by, suppose 1 plus 2a, and this 2a minus 3. Something like this, when you have to do, you will see that this a, which we chose, that a not to be equal to 3 by 2 and a not to be equal to 1, I think, this will satisfy. And the denominator which you are choosing will actually be something related to this a's. So the condition which we started with for matrix to be invertible or not invertible and so on, uh, all this condition will be satisfied. For example, here in this case, a not equal to 1 would play role somewhere, which will actually give me what we need. For example, if you calculate it further, this will be 4a square plus 2a plus 3. And it might come to this, that we somehow got 3 here. So it will be on that line. Okay. So I hope you got the idea. What you got the idea that what we are trying to do here. And now, so once we have this, using this, we can make, let me just write here. Using this term, we can make 0 here and 0 here. And we can also divide by whatever number we get here. It will be non-zero, and we can simply divide by that number. That is this. And you can check that when a is not equal to 3 by 2 or 1, this works really fine. Okay. Or let us, we can solve this actually, but let us solve. This is minus 4a square minus 2a minus 3. Yeah. If I have made any mistake, please feel free to point that out. It was 4, then 2. Yeah, it was fine. So I feel it is fine. But if there are any errors, and then we can just do this R3 going to 1 by this 4a square minus 2a minus 3. And you can check that since a is not equal to 2, a is not equal to 3 by 2, or a is not equal to 1, this actually makes sense here into R3. And then whatever the resultant matrix will be, we will get this. Let me just write this here. 1, 1 minus 1, 0, 1, this 2a plus 2, 0, 0, and this will now become 1 after I subtract and after I divide by the given, and this was 0, 0, 1, this is minus 2, 1, 0, and this is 1 minus, this is 1 minus 4a divided by this 4a square minus 2a minus 3. I'm not writing this very properly, but I hope you understand. 4a square minus 2a minus 3. And the last one is this 1 divided by 1 4a square minus 2a minus 3. Okay, and now using this one here, you can make this to 0. And once we have this to 0, using this one here, you can make this 3, 0. Third row element is 4. Okay, is it? Third row, third element is 4. Only 4, you are saying? This 2a and everything gets cancelled out. That's what you are saying? So instead of 5, you are saying it should be 4 here. Or after resultant, here it will be 4. So let me just point this out. This is my 1 and this is my 2. And you are saying either of these two, air must be 4. So which one needs to be 4? First one or the second one?
First one, madam.
First one? Okay.
Ah,
Oh yes, because we are doing 3 minus 1. So this only 1 here. So yeah, it must be 4. So if this is 4, does that change too much of anything? If this is 4, then rest is fine, right? So this instead of 3, I am getting 2. Oh, I hope 4 minus 2, yes. 2 here. Instead of all this, it will be 2 here. Yeah. But still, if that's the case, a is equal to 1. Yeah, a not equal to 1 is giving me this is non-zero, right? 4a square minus 2a minus 2. So if I put a to be 1 here, this will be 0. So yeah, correct. So note that here that a is not equal to 1. So this belongs to R and is well defined. Okay, so yeah, we are on the right track. Very thank you. Okay, and so yes, this is the scenario which I wanted to point out, that when we do this such divisions here, this the chosen conditions a not equal to a not equal to minus a not equal to 3 by 2 and a not equal to minus 1 would actually be essential for us to arrive at the inverse of a. Okay, and we just saw the example here that a not being equal to 1 was really important for this to make sense. Okay, so yes, that's what I wanted to point out. And apart from that, yes, and you can make the, I mean, I hope you got the idea, like how we are going to move further. This using one. So the next operations will be just subtraction. This will be R2 going to R2 going to R2 minus 2a plus 2 R3. And after that, whatever you get, this R3 going to, yeah, and you can directly do this from here, that R1 going to R1 minus, what is it here? Yeah, R1 minus, not R1 minus, in fact, R1 minus minus 1, not minus, R1 plus in R1 plus R3. And that will give me, this will make, so if I, this will give us 0 here and 0 here. So let me just color them. And the next operation will be R1 going to R1 minus, here I just want to make 1. So R1 minus 2, no, R1 minus R2. And if I, wait, where is it? Yeah, if I do this, I will get 0 here. And you can calculate it. And the resultant terms here will be some star and double star. And here it will be some star. Okay, and you will get the inverse of this matrix A. And once you get the inverse, that inverse would work for any given A not equal to 3 by 2 and not equal to 1. Okay, so, and that's how you will get, so the resultant matrix here will be inverse. Let me call this star. So star will give us the inverse of the matrix A, and it will then give us the unique solution to epsilon. Okay, so we got the unique solution part here. And about the not solution, and yeah, let us just start and we see how much we can do in that case. Because to arrive at, to understand when the system has equation solution, and I mean, we are done with this, that system has exactly one solution in R3. For A is equal to not equal to 3 and not equal to 2, we have exactly one solution. And now there are two cases left. A is equal to 3 by 2 and A is equal to 1. And one of them will give us no solution and the other one will give us more than one solution in R3. That's my guess so far. So let us see. And so when only two conditions are left. So when A is equal to, let us start with 1 because it's easy to calculate. This is 1, 1, minus 1, 3, sorry, 2, 3, 2, because 2 into 1, 2 into A, but A was 1, so it is 2. And now it is 1, again 2 into 1, that is 2, and 3. And here I am getting 1, 3, 2. And now I will try to solve this system of equation. I hope this one was correct one. The calculation I did here. This is correct, right? This so far, there is no error here, I assume. And that's why I'm choosing this A to be 1, and let us see how we get, what we get. So I again have to make this R3 is equal to R3 minus R3 minus R1, and R2 is equal to R2 minus R1, and I will get 0 here R3 minus R1. So 2 minus 1, 1, 3 minus minus 1, 4 here. And here it was 3 minus 2, that is 1. And here it was 2 minus minus 2 is 2 plus 2, 4. And now here I am having 2 minus 1 and 3 minus 2. And now in this case, I have this condition minus 1, 1, 1, this. I can subtract the whole row. I mean, here what I'm doing is R3 minus R2. And this is now has become system of two equations in three variables. And you can see there will be infinitely many solutions in this case. Okay, so this is, we anyway have to find the system solution to, so understand that the way we are arriving, I mean, we are trying to tackle the problem here, we are actually also solving the second one. Because see, the moment we found this A inverse here, and we did not actually calculate it, but the process which we were doing, which would have given us the inverse of matrix A, we would already be answering the question to the second part, where exactly one solution and what that solution is, A inverse B. And in that case, we got the answer. And the more than one solution part is when A is equal to 1, which we are now actually obtaining the answer to. So now this is x plus y minus z is equal to 1, and this is x plus 4y is equal to 1. And this will give me x is equal to 1 minus 4y. And the moment I have this, x is equal to, substitute if I call this 1 and 2. 2 implies x is equal to 2, this 4y, and this imply this 1 minus 4y plus y minus z is equal to 1. This will give me this z is equal to, let me write this first, 1 minus 3y minus z is equal to 1. This will give me z is equal to minus 3y. Okay, and this is infinite solutions which we wanted. So infinite solution is when for a is equal to 1, infinite solutions, x, y, z is, I'm writing, so is actually 1 minus 4y, and what we, y is as it is and z is minus 3y. And note that if I try to separate it here, 1, 0, 0 plus 4, 1 minus 3y, this is particular solution of this system. And if you remember, if you read the assignment sheet properly, there are so many, I mean, it's 12-page of PDF, which contains so many things. And if you see, I mean, this is the particular solution which we talk about. And the moment I vary this y here, I will be getting infinitely many solutions to this system of equation. And this here is exactly what we say. This is a solution to this system where this A is similar to what we have in earlier, I mean, the A which we have here so far. Okay, and if we see whether this makes sense, is I hope I'm correct here and I did not make any mistake. It's correct, right? I hope people were with me. Because is this really solution? Because if I put y is equal to 0, this becomes 1, 0, 0. And is 1, 0, 0 solution to this? 1. This is 1 minus. No, 1, 0, 0 is not solution to this. 1 minus 4y.
It's minus y.
Where?
In the last, it should be minus 4.
This one?
In the last line, it should be minus 4, 1 minus 3. In the last line.
Which one? This one? This one?
Down, further down.
Yes, here.
Yeah, because it is 1 minus 4y, 1 we have taken out. Minus 4y, that minus symbol should come with minus.
Okay, yeah, minus 4y is okay. But see, what I was saying is the the way I vary y, it will give me new solution every time. So if I put y is equal to 0, so when we change y, we must get solutions, right? To ax is equal to this b. And if we choose y is equal to 0, because uh, depending on y, my x and z are changing. So if I choose y to be 0, this particular solution becomes 1, 0, 0. But that here is not a solution to this. Oh, sorry. See here, so that's the mistake I made. This is not x plus 4y. This is y plus 4z is equal to 1. And that's why it was a mistake. So this then becomes y is equal to 1 minus 4z. Y is equal to 1 minus 4z means my x plus 1 minus 4z minus z is equal to 1. Yeah, now it will be correct because I made a mistake here. Now it is x is equal to 1 plus z minus 1 plus 4z, and this is x is equal to 1 is gone, 3z, 5z. Yeah. I hope now it is correct. So now my x is 5z, z is as it is, and y is 1 minus 4z. And now this particular solution becomes this 5 minus 4, 1, z, and this is now 0, 1, 0. And now is this a solution? Yes, exactly. So see this. So the solution which I got 0, 1, 0 is the particular solution actually satisfies this equation. Okay, so what we are doing is actually correct, and it actually, so now this y is equal to 0. It should not be y is equal to 0. It must be z is equal to 0. The choice of, when we change z, the choices of z must give us infinitely many solutions. Is this okay now? So our solution which we found is correct. and this particular solution, and this is zero space and everything, which if you read the notes properly, even the assignment sheet which is given to you in purple or violet, I don't know the color name, but whatever that is, please read that, and it has everything which I discussed here. Okay, and now the final condition. Final condition means not final condition. The only possibility for A to B, and when A to B 3 by 2. Let us see then what my system of equation is. Then it is 1, 1 minus 1, 2, 3. 3 by 2 gives me 3 here. And here it is 1, again 2 into 3 by 2 giving me 3, and 3 again here is equal to 1, 3, 2. Okay, and sorry, this XYZ here, I hope I wrote that in earlier when I wrote the system previously. No, I directly wrote the augmented matrix. So let me write that again here. So yeah, so now I need to again do row operations and check what I get. I mean, we could also get infinitely many solutions here also, but let's see. So again, this R2 going to R2 minus 2 R1, and R3 going to R3 minus R1, and I will get 1, 1 minus 1, 0, 0 here, 1 minus R2 is 1 minus 2. So 3 minus 2, 1 here, and now 2 minus 1, 1 here. That's not a problem. Now 1 minus 3 minus 2 is 1. 3 plus 2, 5. 3 minus 1, 2. 3 plus 1, 4. And now I am making this 0. So R3 going to R2 minus, sorry, yeah, R3 minus 2 R1. And I'm getting here 1 minus 1. Here it is 0. And for 4 minus 10, what is it? Minus 6. And here it will be?
Should be plus 6.
Should be plus 6.
Yeah, because minus 2 R1 will become minus 1. I mean 2 plus 2 and 4 plus 2, 6.
Before that, is this correct here? What I did? This calculation is correct so far, right?
Yeah, looks like that.
Looks like, yeah. So, yeah, I mean, here if I get 0, this 4 minus, 4 minus 10, it should be, no, it will be minus 6, right? Because this is 4 minus 10. It will be minus 6. And this is 1 minus,
Actually, R3 is R3 minus 2 R1. So R3 is 4 and minus 2 R1 will become plus 2.
2 R1. No, sorry, I made a mistake. It
2
is,
plus
it
6.
must be
Acha,
2
okay.
R2. Oh, 2 R2. Yes. Because if we are using R1 in that case, then this becomes non-zero. So we don't want that. So this is the case. We use this to make this one and this one 0. We use this, let me use the other color. We use this to make this 0. And whatever here it's left, we divide it by whatever non-zero term left here and use that to make here 0 and here. And I mean, that's how the, what we say, plan of action goes from one to next step. Because once we use R1 to make this entry 0, then again this 1 will give me some non-zero term here. And we don't want that because we already made some effort to make this 0. Okay, so whatever here, we will get some star here. And this clearly, I think, has unique solution. Not unique. Will this have infinitely many solution? I doubt that. Because if this has unique solution, then this would land in the first case. So did we make any mistake here? That's my concern at this moment. Let us see. So this minus 6, and here I get 1 minus 1 minus 1 minus 2. This is minus 1. And the moment I have this, I get minus 6z is equal to minus 1, and this gives me z is equal to 1 by 6. And I mean, in this case, the system will have solution, right? And if the system has solution, then it has to land in, because this will be unique solution, because this this z will give me exactly, I mean, z is equal to 1 by 6 is fixed value, and the moment I have this, the y will be fixed, because from here I have y plus 5z is equal to 1. So the moment I put the value for z here, y will be some unique term, unique value, and since these two are unique, x will be some fixed number. So this gives me unique solution to this system of equations, but I did not want that. I did not want that. I hope you got what I'm trying to say here. I did not want this system to have a solution. I mean, from what we have calculated so far. Because if system has to have unique solution, then A must not be equal to 3 by 2 and A must not be equal to 1. This is correct, right? 2A minus 3. Oh, see, here I made a mistake. Here it must be plus 3. So this must be minus 3 by 2. And now again, see, that's why we got the wrong answer here. So minus 3 by 2 would give me here minus 3, here minus 3. And now the whole game changes. I hope you got what was the mistake. So yes, the theory never fails. So if we say this must be plus here, and that's why this A must not be equal to minus 3 by 2. And once I have that, I'm pretty sure this system will not have a solution in that case. This minus 3, this is okay. This will change. Yeah. I mean, you can take here. This will not have solution. I will just write it in this system will not have a solution. Or since we have only little time left, let us just solve this and see that it really does not, because if we start new question, we anyway won't be able to solve it completely. So we have few minutes. Let us see that this indeed does not have solution, or it will not have any solution, or infinitely many solution. Whatever be the case, we don't care. But let us see that 3 minus 3. So I want R2 minus 2 R1. So R2 minus 2 R1 will give me 1 here. Minus 3 minus 2 will give me minus 5. No, see, minus 3 minus minus plus 2. So this is minus 1. And here minus 3 minus 1 will give me minus 4. And this is 3 minus plus 1 will give me 4 here. And here we have 1, 1. And Next, 1, 1 here. This 1 minus 1, 0, minus 4, 4. And if yes, see, we got it. So if I do R3 going to R3 divided by minus 4, then this will give me this system: 1, 1, minus 1, 0, 1, minus 1, and 0, this 1, and this minus 1. And here I am getting 1, 1, minus 1 by 4. And if I subtract, now R3 is R3 minus R2, I will get 1, 1, minus 1, 0, 1, minus 1, 0, 0, 0. And here, this is 1, 1, and does not matter. I think it is minus 5 by 4. Whatever it is, this is non-zero. And now the system does not have solution. So, yes. So, hence, the system does not have solution in this case. Because, see, whatever value of yz you substitute here, because this equations becomes what? 0x plus 0y plus 0z is equal to minus 5 by 4. Not possible. Is it okay? What we did, I hope you got the idea that whatever we did so far is actually correct. And all the conditions we got for a is equal to. So see, for us to get a solution, and whenever we have such kind of questions where the solution depends on this a, and a belongs to R, so each value of a, either it has solution, it does not have solution, or it has infinitely many solution. So for exactly one solution, there are only two, there are infinitely many choices except for this minus 3 by 2 and not equal to 1 here. Whenever I choose a not equal to 1 or a not equal to minus 3 by 2, I will have a unique solution. And now only these two possibilities left, that a is either minus 3 or a is equal to 1. And we saw that when a is equal to 1, we get infinitely many solutions. This infinitely many solutions, we got the particular solution here, and this is corresponding a solution to corresponding homogeneous system of equation. And when a is equal to minus 3, we got that the system does not have any solution. We got this weird kind of condition here. So I hope this was clear to you. We use row echelon form to understand the solution of system. This third question gave us everything. We could see the conditions on A, which gave us all the three possibilities for the solution. We also tried to find the inverse of a matrix to obtain the unique solution, and we saw how the Gauss elimination works to obtain the solutions for the given system of equation. So, any doubts here? And about the questions which were asked in the last session about the exam, whether the exam will be subjective and objective. So I hope you saw in the discussion forum that the exam will be subjective, and there will be true false kind of questions in the exam. So yes, you can prepare accordingly. Okay, and thanks. Any doubts, please let me know. Otherwise, we are over time. We can end the session.
Yeah, this is Nitin Rai, login as Swarnika Rai.
Yes,
Uh,
yes, yes.
Actually, I joined late because I was first tried to join by my mobile. It was not connecting to
Okay,
Zoom.
okay,
Link was
okay,
issue. By the time I
okay,
reach
okay,
home, I just could join last 20 to 25 minutes.
okay,
Uh,
okay, okay.
so this first question, I can handle it with this kind of
Hmm, hmm,
solutions
hmm,
suggested.
hmm, hmm, hmm,
Can you
hmm.
explain a little bit about the second assignment question, just to explain actually what it is trying to ask?
So, About the assignment questions, actually, we are not supposed to discuss this because you will be graded for that
So
questions.
for similar
But
kind of
yes,
assignment, did we cover in this session so that I can
no, no,
just,
no, 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 not the second camp. You mean the 3.7A and 3.7B of the assignment sheet, if
yeah,
I'm not
I think the
mistaken.
last question, yeah.
Yes. So for that, I will suggest you to read the whatever given in the first, the purple or violet color theory. And if you try to solve these test exercises, T.31, T.32, if you try to solve those assignments, I mean those questions in the assignment, I think you will be able to solve this. And let me just read this system of equation so that U is subspace of K. I mean this, if I'm not mistaken, this very question U is equal to whatever given if L of epsilon is non-empty. That U is equal to is non-empty is a subspace of K. I mean, the hint is already given to you, so I think you can read and expand it, and it would help. And if there is any doubt, I mean, you can submit the assignment, and if there are any doubts, since this is assignment question, I can't discuss it explicitly now. But yeah, I think hint would help you. And if hint is not helping you, and if you could not solve the question and submit the assignment, maybe raise the question in the discussion forum. Uh, Either we will try to provide the written solution, and if that's not possible, we can discuss the solution in the next tutorial session. But we are strictly told to not to discuss the questions which will be submitted in the assignment explicitly.
Okay.
Yeah. And apart from that, if you have any questions, please feel free to ask. Really sorry, but we are, I mean, we are strictly told
That
to
is
not to
fine. That is
discuss the
fine.
question. Yeah, yeah. Yes.
3.4, I can,
Mhm.
actually, I have joined very after.
Yeah, for that, for this tutorial session, which whatever I have conducted, you can get the notes within maybe 10-15 minutes. I will try to provide the notes. The video, uh, it will be available by midnight tonight.
By midnight tonight. Huh?
Yes, I will upload the video uh, maybe in I mean I will upload the video link in that
Fine, fine, yeah.
yeah, you know where the problem session port like
Yeah,
tab is there in the
last time also
yes,
you have uploaded the video there.
yes. All the videos and all the notes are there for my tutorial session there. Even the last two tutorials and it's video and notes. For this, I will upload the quick notes for now, and you can access those there. Yeah,
Okay. Okay.
yeah, sure.
Usually
Thank
this,
you. Yeah, sorry.
usually this kind of this helping session will be one day before the submission date, or it can be at least 2 days prior. If I mean,
So, I mean, we once fix the time, we can't change it. I mean, it is
okay,
us
okay.
who choose it, and I mean, one session happens, yes, I mean, on the Mondays, and if that's helpful to you, or if you think that that would be helpful to you, and can give you more time to to understand the assignment, uh, you can try to attend those. And if you can't, I mean, there are two sessions because those who can't attend it on Monday, I mean, they can attend it on Tuesday.
Acha,
So
acha, okay, okay.
yes, and you can attend both. It's not compulsory that you have to attend only one of those. So it's up to you. So yeah. Apart from that, any question related to what I did today, if at all you have it.
If I, okay, if I need to get some clarification, can I put on the announcement chat, or I have to?
Sure. You can put it in the discussion forum and people will be there to help you. I mean, you saw that about the exam for exam type and everything, the question was answered to you immediately. If not immediately, I mean, these questions are answered there by respective teams. So you can definitely raise all your queries. Every doubt you have, you can definitely post it there, and there are people who would try to help you. Yes, definitely.
Okay.
Yeah, sure. Thank you. Bye.
Thank you very much.